Can you see the screen?
Yes.
So hi everyone, I'm Harsh Kushwaha. I'm the former president of the CP division of the programming club, and I'll be talking to you about number theory. This will be really a short lecture, and we'll be covering four basic topics here. Basic primality testing means uh, to check whether a number is prime or not. Then sieve of Eratosthenes. This is just a way to. This is just a fast way to give all the prime numbers from a range to us. The fastest way to do it. Then we have prime factorization. We'll return a vector that has all the prime factors of a number through factorization, and then we'll learn about basic modular arithmetic. So as I said, in primality testing, we check whether a number is prime or composite. So basic algorithms for it are brute force, obviously, and then square root method, and then using sieve and other heuristic and probabilistic methods. This is the code for brute force. In brute force, we just run a loop from 2 to n minus 1 and then check whether the number is divisible by any of the numbers in this loop, uh, as you can see in this code. So if the number is divisible, if mod I is 0, then we return false, that the number is not prime. And if not, then we return n greater than 1, because uh, for for case of 1 this will return true, right? But we want for case of 1 false. That's why we have put this condition n greater than 1. Any doubt in this brute force code?
Oh, yeah.
Uh, then we have square root method. This is an optimization over brute force. Here we only iterate from 2 to root n, and rest everything is the same. So here's the reason why the square root method works. Because if we have a number n that is not a prime, then uh, it can be factorized into two values such that a into b equal to n, right? Any doubt in this statement?
No.
So therefore, now one of these two numbers have to be greater than root n, because otherwise the product will be greater than n, and the
Yes.
other factor will be smaller than root n. So even if we check from 2 to root n, we'll get one factor if it is composite, and we'll get the n mod I equal to 0. So all we have required to do is just check from one root, and so what it does is it reduces our time complexity from n to root n. So suppose we have a big number from in the range of 10 raised to 9. If you want to check if it is prime, then you will get TLE, because you can do 10 raised to 9 steps. But if you use the square root method, it will get done in 10 raised to 4, 10 raised to 5 time complexity. So this is the sieve method. Sieve method is an even efficient way to find the prime numbers. It has the complexity of big of n log of n. So the way this works is, if we have any composite number, it must have a prime factor such that p less than c. This is very obvious fact. And then what we do is we repeatedly find the first number that does not have any prime factors. If it does not have any prime factors, then that number must be prime. And we'll take this prime and we'll mark the multiples of the number as composite. We'll run a loop to find all the multiples, and we'll mark them as composite. So we'll have a look at the code. Uh, so this is the array where we store. This is a Boolean array where we store whether the number is prime or not. It will contain indexes from 0 to n, but what we want is 1 to n. So we'll initially fill the array with true, and then we'll initialize these two values as false because these are not prime, right?
Can you explain the means what's the logic behind the Sieve of Eratosthenes that I
Oh,
didn't get?
okay, I'll explain it once. So, in here, what we have to do is we have to mark the numbers which are not prime, right? You can understand it this way. You have to mark the numbers which are not prime.
Okay.
I'll explain you through the code as well.
Yeah.
So, what we initially do is we mark all the numbers as prime. All right. After the
Okay.
in this fill step. So after this fill step, what we have to do is we have to mark the composite numbers as false. All right.
Okay.
So basically, we have to find all the composite numbers.
Acha.
One way of finding the composite numbers is take all the primes and find out all its multiples, right? Because in this way, you'll cover all your composite numbers.
Could you repeat that statement?
You could take all the prime numbers and find out all their multiples in the given range.
Okay.
Then
Yeah. Then we can get a composite number.
this way you'll get all composite numbers in that range.
Okay. Yes.
Hmm. So that is exactly what we have done here. So from 2 to root n, if we get a prime number, then we run another loop. And if we run another loop which has a multiples of this prime number, right? Now j will be multiple of I, as you can see in this loop. And then we mark all the multiples of I as false. That means composite.
Uh, so in primes n plus one array. So at say primes one is stored, primes two is stored like this. The
Yes,
array is
yes, yes.
okay.
Any doubt in this code?
Uh, could you give a small example? I think that would be more clear.
Okay, okay. So I just try run the code here. Just show you. So for example, let us let us suppose take we feed here 4. All right.
Hmm.
We run C4. Uh, First two lines are obvious. It will fill the array with true. All right.
Hmm. Hmm.
Then we have prime 0 and primes 1 as false because these are not prime. They are neither
Hmm.
prime nor composite, right?
Hmm.
Then we run a loop from then in the first iteration I equal to 2, right?
Hmm.
Then if primes I, so this will this will return true.
Primes two, yes.
Yes, because 2 is a prime
By
number.
default.
Hmm,
Yes.
by default. Now, in this inner loop, what we do is we take all the multiples of 2. So j is initially I into I.
So okay,
Hmm.
and then j is equal to j plus I. So
Yes. 2 first,
four.
4, then
Uh,
6. If the range
yes.
is big, 4, 6, 8, all the multiples of 2 will be marked as false because they are composite, right?
Yes. 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 Okay. Okay. Yeah, I
Similarly,
get it.
in the next step, 3 will be all the multiples of 3 will be marked and so on.
Oh, and this fill is a function to fill the array, right?
Yes, yes.
Which you have not shown here.
Yeah, it is an inbuilt function. You don't have
Okay.
to type it.
अच्छा ठीक है. Okay.
I'll also explain you these limits. Why are they here? So I into I is less than equal to n means we are only iterating from 2 to root n. Because in this way we'll already get the prime numbers from 2 to root n. We don't need the prime numbers greater than root n because they will be covered here. Because j equal to I into I, so j equal to I square, right? So all the numbers from I square to root n will be covered here in the second loop, in the inner
Okay.
loop.
Okay. Yes. Yes.
So this is how we get the time complexity. So as you have seen, we take every prime number and we find out all its multiples, right? So this will be the time complexity at each step. So at first step it will be n by 2, n numbers, and every second number is a multiple of 2. Then n by 3, n numbers, and every third number is a multiple of 3, and so on and so on. Right? So uh, this will be n into this prime harmonic series, 1 by 2 plus 1 by 3 plus 1 by 5. Now this sum comes out as log n. There will be a proof on the internet, but this the result, that this sum comes out to be log n. So the value of this, for suppose n equal to 10 raised to 7, is just 2. All right. That's why it is an efficient method, because for n equal to 10 raised to 7, the time complexity will just be 2n for the Sieve method. Uh, any doubt in time complexity?
Here log n is base 2.
Yes.
Okay.
Then we have prime factorization. Prime factorization, as I said, is finding all the prime factors of a given number. So there are three main methods for it: trial division, wheel factorization, and sieve method. We'll be covering only trial division in this lecture. Trial division is the most basic method of prime factorization. We'll just iterate from 2 to root n and um push back all the factors of the number in a vector. So this is the code for trial division. Uh, Here is a parameter n, of which we have to find the prime factors. We'll store all the prime factors in this vector facts. So we have this for loop. We iterate from 2 to root n. And for every divisor d, we uh, if the mod d is 0, if d is a factor of n, we push back d in the facts vector, and then we divide n by d. This is similar to the method which we used to find the prime factors by hand back in school. We just keep dividing the number n by d and then store the d in facts vector. Any doubt in this part? For loop part.
No, clear.
Hmm. So finally, after all the divisors up to root n have been found out, uh, we'll see if the we'll see if n after all the divisions is 1. If it is not 1, then that number n will also be a factor of the initial number, right? So we'll push back that number too. So for example, if we have put n equal to 3, so this will not in this loop, there will nothing that will get fed in the vector, right? The vector will be empty because it only runs through root n. So here n will be equal to 3, but 3 is a factor of 3, right? So we push back 3 in the facts vector. Did you get it, why we use this?
And here we are running till root n because of the same reason you told in the uh, first few slides, right?
Yes, yes.
Okay.
Any other doubt in prime factorization? Okay, then I'll move ahead. Then we have modular arithmetic. Modular arithmetic are mostly used because in some cases the answer is larger than 10 raised to 9. or in that range. So we don't want the solution to overflow. So what we do is we take the mod of the answer, uh, mod of 10 raised to 9 plus 7, or mod of any other prime number, so that we still have the answer and it doesn't overflow. Uh, but in these cases, we need to understand um, how to add, subtract, and perform these mathematical operations when modulus is involved. So these are the basic formulas. In modular addition, we have to do is understand that if we have two numbers and we need to add them and take a mod, we can take the mod of those two numbers first. So the reason why this is required, because let us suppose a plus b are very large numbers, right? From the range of 10 raised to 9, 10 raised to 9. So if we add those two numbers first, they will just overflow, right? And it will give us a junk value because they are not in the range of int if we add them. But since we need to output the answer in mod, you'll be given in the question that you need to output the answer in some numbers mod. So what we can do is we take the number a and then take out its mod first, and then take the number b and take out its mod. Uh, these numbers will be selected in such a way that now a plus b, a mod m plus b mod m will be within the range of int, so it will not overflow.
So the question is asking to give the answer in its mod value of some number, means
Yes,
percent.
yes,
Okay,
yes,
okay. So that we can give an answer which is not overflowing.
yes, yes.
Okay.
And then we finally add these two numbers and take the final mod. Exactly same rule applies in subtraction. So the reason it's written be very careful when using C++ is because C++ mod rules work a bit differently. So let me show you. Here I've written -7 mod 4, right? So in C++, the answer for this will be -3. Now suppose if we want one, because both are legitimate answers, right? -3 is also an answer, and 1 is also 1 also can be an answer for this, because -7 can be written as 4 into -2 plus 1. So 1 can also be an answer for -7 mod 4, right? So what if we want that? What if we want a mod to be always positive? In C++, the mod of a negative number is always negative or 0. So if we want our mod to be positive always, we do this. We just add the number which we are taking the mod of to the result, and then we take the mod again. So this will give us the required answer 1. So in many cases you'll have to do this. You'll have to uh, find out whether the number that you're taking mod of can be negative, because this won't be hard coded to you, right? In the test cases, there will be a different n, there will be a different x that you have to take mod of. So you'll have to find out whether it can be negative or not. In cases where you want the mod to be always positive, you want the remainder to be always positive, you do this. You add the same number n and then you take the mod of it again. So this is in C++. In Python, we don't have to do this. In Python, if I show you, uh, this will give us the required answer. In Python, mod is positive. Understood the differences?
Yeah, so is it the like the can be the requirement of the question to want a positive value only?
It might not be written in the question explicitly. You'll have to understand what the question wants or what you have to do to get to the required answer
Okay.
in most cases.
Okay.
So exactly same rule applies in modular multiplication. Any doubt in this modular arithmetic?
It's clear.
So we'll have a look at some problems. Take some time to read this problem and then tell me the approach that you're getting. Anyone thought of any approach?
Yeah, means even we can do that. If a number is even, then we can do 2 plus one number is.
So the question is simple. We have given an integer that is greater than or equal to 12, and we have to express it as a sum of two composite numbers. Any two composite numbers will be fine. What will be the brute force approach for it? Brute force approach is simple, right? This is correct. For even number, we can do n minus 4 plus 4. And for odd numbers, so did you understand? Did everyone understand why n minus 4 plus 4? So 4 is a composite number, right? And the number is always be greater than or equal to 12. So the other number will be 8, 10, like that, 8, 10, 12. So it will always be an even number, which is greater than 2. So it will always be a composite number. So we'll have our two composite numbers if we take 4 and n minus 4. Similarly, can you figure out the number for if the n is odd? Or if anyone has the approach for the brute force solution. Okay, I'll explain the brute force solution first. Uh, the brute force solution is simple. We just take the integer n and we take all the two numbers that it is the sum of. So we take 1 plus n minus 1. So example, we have 14. So we take 1 and 13. We take 2 and 12 and so on in a loop. And then we check if both numbers are composite or not. So the check for that is simple, right? We just run a loop from 2 to root n, and we check if n mod I equal to 0. If n mod I is 0, then the number is composite. So we check if both numbers are composite. As soon as we have the two composite numbers, we output them. This is the brute force solution. The optimal solution is taking the n, and if the n is even, we take n minus 4 and 4. We don't have to check anything. We just know that 4 is composite and n minus 4 will always be composite if n is even. Um, so anyone got the approach if n is odd? Or I'll explain it now. So if n is odd, we can just take n minus 9 and 9 as the two numbers because 9 is a composite number, right? and n minus 9 will always be composite because if n is odd, then we get numbers like 13, 15, 17. So n 9 we already have, then n minus 9 will be 4, 6, 8, etc. So 4, 6, 8. Even numbers which are greater than 2, they'll always be composite. So we'll have our two numbers as 9 and n minus 9. Any doubt in the solution? So basically our final solution will be just checking if n is odd, see out n minus 9 and 9. If n is even, see out n minus 4 and 4. Any doubts? So let's have a look at the next problem. Have a look at this problem and tell me if any of you has any approach. Here we have to simply check if the given number n has any odd divisor. Try to think of it in terms of the prime factors of n. Suppose you have all the prime factors, right? All the prime factors of the integer n. Then can you check if it has an odd divisor? So here we try to take all the prime factors of the number n. So suppose the number is 8, we have the vector as 2 comma 2 comma 2. Suppose the number is 10, we have the vector as 2 comma 5. So what we know is in the prime factors vector, there will be either 2 or an odd number, right? Because 2 is the only prime even number, right? So if the vector uh, has any number other than 2, it will be odd. So what this means is if the number n is not a power of 2, it will always have an odd divisor. Any doubt in this? Because 2 is the only prime factor that can be even. All the other prime factors are odd. So all we need to check is that n is a power of 2 or not. So for this we keep dividing n by 2 until it is even, and then if the result is 1, then we have our answer that n does not have an odd divisor, and if the result is not 1, then it does have an odd divisor. So this will be our solution. Any doubt in the solution? Okay, everyone else? So I think it is clear if no one has any doubt. Uh, so the rest two problems I'll expect to you to do them by yourself. This PPT will be made available to you, and these are some resources that you can check on some topics that we covered today. So this was a lecture. Any doubts, if anyone has in general, or any questions?
No, but it's clear.
Okay then. Thank you everyone.
Thank you for